Good morning, students. So today we start with a new topic, flow control and reliable transmission. So for this topic, I follow the book by William Stallings. And again, as I was mentioning in the beginning of the semester, you can follow any book, other books if you find it easier for you to follow, okay? But try to follow the convention or notations which I follow here, okay? Because some books follow slightly different convention, although the underlying technique remains the same. So let's start with flow control. So this flow control, what we study here is at layer 2. It's a layer 2 function, and this flow control is also carried out at layer 4, okay? And at layer 2 it is optional. When I say layer 2, that is, these functions are carried out at every link basis. Okay? Layer 4 means it is carried out between the end host, our computer, and the remote server, something like this, between the end hosts. Layer 2 means the function is carried out at every link level. Yeah. Now, what is a flow control? So the problem can be easily understood. Let's say there is a sender and there is a receiver which is connected by a link or by a connection. So when we say it's by a connection, so then we refer to layer 4. When we say it's connected by a link, we refer to layer 2. Okay? So sender is sending frames. Okay, note that we call the packets as frames at layer 2. The sender is sending frames to the receivers at a certain rate. Certain rate means, let's say per second it is sending 100 frames. Now, there are two things which we need to note, whether we have adequate bandwidth or link data rate to carry these 100 packets or 100 frames to the other side. Okay? Yes, we may have adequate bandwidth, there's no issue, but in addition to that, these 100 frames per second need to be processed by the receiver. Suppose the receiver is slower when compared to the sender. That means what? Let's say the sender is producing and sending 100 frames per second, and if the receiver is not able to process 100 frames per second, then we say that the sender is jamming the receiver because sender is too fast. Note that all the 100 frames have reached the receiver. There's no problem on the bandwidth. Okay? This is something like the road condition is clear. Okay, so you are able to reach some place where you want to go, let's say mall or something. But at the entry, okay, the processing is slower, so there's a delay there. Is that okay? So similarly, here bandwidth may be adequate, but if the sender is faster and the receiver is slower in processing those frames, okay, then the sender jams the receiver or the sender overwhelms the receiver. This would lead to buffer overflow at the receiver. Okay? So receiver keeps certain amount of buffer to handle this problem, but it may so happen that buffer can overflow, so in that case, the frames need to be dropped. I usually give this analogy. Again, it's an analogy. Okay, let's say I'm dictating a paragraph. I ask you to write it down. I'm reading a paragraph, and I ask you to write it down. Reading is faster. I can read the words faster, correct? When compared to your writing speed. So if I keep on reading, let's say word 1, okay, if sender is faster and receiver is slower in processing, and I ask you to write it down, what will happen? Bandwidth is okay. You are able to hear whatever I read, okay, something goes into your mind, right? But whether you will be able to write it down. That's okay. Initially, okay, if sender is fast, okay, few words you have written, but you will be writing, let's say, 5th word. At that time, I will be reading 8th word or a 10th word, right? So you have some buffer. Some words you can keep it in your brain. You can write it down, but after some time, you are lost. After some time, you are lost. You are not able to handle it, right? This is something like, I am jamming you. I read quite fast. I ask you to write it down with my pace, okay? So how we can solve this problem? This issue is called the flow control issue. We need to solve this problem. So there are broadly two approaches. Okay, one is stop and wait based approach, the other one is sliding window based approach. So before we go into the details, so let's quickly look at the timing diagram, okay, which also depicts or shows the model of frame transmission. Basically, we consider two models. One is error-free transmission. Okay. Let's first assume that there are no errors. How this issue is handled? When there are errors or losses of frames, okay, how the flow control issue is handled. But in the case of errors and losses, in addition to the flow control, we also need to make sure that the transmission is reliable. It's actually not reliable because already there's a loss or errors. To make it reliable, on top of that, we need to carry out some additional functions. Okay? Like maybe if the receiver detects an error, it has to ask the sender to send it again. So what's the best way of doing it, right? And what type of messages are involved? What kind of protocols can be used? So that mainly is carried out in this case of errors and losses. Okay? So you can show here, I mean, sometimes we put this horizontally, sometimes we put vertically, but what's important is to note down, okay, the x-axis and y-axis, the vertical and horizontal axis. Here, time flows vertically from top to bottom. So frame 1 is sent here, frame 1 is received here, frame 2 is sent, frame 2 is received. So note that frames may be sent continuously or there can be some gap between them. It may be because of the protocol or because that the sender, at the sender side, there's no frame available to be transmitted. Okay, so don't think that always, okay, of course, when we derive some simple expressions, we will assume that the sender has sufficient number of frames to transmit, right? Yeah. Then in the second case, we distinguish between the errors and losses. Sometimes protocol need not differentiate, but still we need to know the difference between error and loss. Error means the frame has been received by the receiver and it is recognized by the receiver that it is a frame. And at the same time, the error detection mechanism, let's say CRC test, which we discussed in the last class, okay? CRC test fails. That means the receiver knows that some bits are corrupted. The frame is damaged. There are some errors. The frame is damaged. Now there is another case when the frame propagates through the channel, it was heavily damaged by the noise such that when it reaches the destination, okay, receives some bits here and there. The destination is not able to even recognize that it's a frame. Some signals are received, some garble, something, right? So it's not able to recognize that it's a frame because it was very heavily affected. So in that case, we say that the frame is lost. The frame is lost. That is, the receiver is not receiving it. So when we discuss the protocols to deal with reliable transmission, we will differentiate these cases in some scenarios. Okay. Now, as I said, there are two approaches. One is stop and wait. The next approach is sliding window-based approach. Stop and wait approach is very simple to implement. Again, we go back to the analogy. I'm reading a paragraph. I ask you to write it down. The simple way for me to slow down or to impose flow control is that I read out the first word. I just read first word, source. Then I stop. I wait for an acknowledgement from you. Okay, prof, done. Then I read the second word. Then you raise your hand. That means you have already written it, right? Then I read the third word. So for every word, I wait for an acknowledgement from you to proceed further. So that will solve the problem, right? I will not jam you. Whatever I read, you should be able to write. Because for every word, I wait for an acknowledgement from you to get a green signal from you that you have already written that word. Is that fine? So similarly here, the sender first sends a frame, transmits a frame, okay? And after some time, the receiver receives the frame, and the receiver will respond with an acknowledgement. This is something like I read a word, I ask you to raise your hand once you are done, right? what the sender does is it will wait for the acknowledgement before sending the next frame. Before sending the next frame. The destination, if it is slow, if it's not able to cope up, okay, if the processing is slow, the destination or the receiver can always stop the flow, always tell the sender, don't send new frame. How it can send? Very simple, by not sending an acknowledgement. Let's say I read a word. If you don't raise your acknowledgement, that means you are slow. You don't need to tell that, Prof, I need more time to write it down, right? If I don't receive an acknowledgement, that means you are asking me to wait for some more time. The implementation wise, it's very simple. So if you look at the timing diagram, a frame is sent, then at this point, let's say ACK received, then another frame is sent, then when an ACK is received, next frame is sent. This is called stop and wait. Stop and wait, is it a good idea? So the advantage is that it's very simple to implement. In the lab also, you are going to implement some stop and wait or some variant of stop and wait. Okay, it carries only 15 words. I don't want to give you a more complex problem like sliding window and other things. Okay. So the problem is this: if you transmit or if you send small number of frames, that's fine. Okay, for every frame we can read. That means if I read a short paragraph and I wait for every word, I read out a word, then wait, then read, that's fine. But if I need to dictate a big paragraph, that's not a good idea. Similarly, if the sender wants to send a large number of frames, then stop and wait has its own limitation. It's not good. It's inadequate. Okay, right? It has its own limitation because it takes more time to complete the transfer. Right? Then, why sometimes we need to send large number of frames? For that, we need to answer this question. As I have been telling from the beginning, the data is not generally sent as a single piece of payload, single piece of data or packet. Okay? Usually the message, which is large, is sent divided into small number of packets, a number of packets. Okay? See, for example, you take a file or you take an image file, okay, or video file or movie file, okay, or any email text, short text is okay, but if it becomes longer and longer, then the message may have to be split into small number of frames, sometimes large number of small number of frames. Okay? Why we should send a small number of frames? So there are few reasons. Okay? One, okay, the reasons are not listed in the order of importance, but why I should send a small frame? Why not a big frame? Of course, in tutorial 1, we have already seen an example, okay, where when you send short frames, we can send the transfer faster, right? There are other advantages as well. Limited buffer size. Okay, that's also related to the problem because the store and forward switches are the routers. They are basically store and forward switches or routers. Okay, that means the entire frame need to be received before we start transmitting on the next line. So if the frame size is bigger, then we need to hold a buffer to hold a bigger frame. Okay? Next, errors detected sooner. That means if our frame is quite big, let's say 50,000 bits, then in order to calculate the CRC, okay, you need to carry out the division over 50,000 bits. Right? If the frame is shorter, the CRC can be computed faster and errors, if any, can be detected sooner. That's what it means. On error, this is very important reason. Retransmission frames are small. If you send a very large frame, let's say 50,000 byte frame, for example, okay, even if one bit is corrupted, you need to send again another 50,000 bytes. But if you send 1,000 byte frames, even if one bit is corrupted, you will be retransmitting only 1,000 bytes. Right? So for that reason, we want to have the frames small. And in the case of Mac, that is when medium is shared by more than one, okay, if the frame size is quite big, then one user is using the medium for a long time. because usually the other user will wait until the transmission is complete. So we don't want one user occupy the medium for a long time because he is transmitting very big frame. For these reasons, we send small frames. That means the number of frames will be large. That means stop and wait is not a good idea to use all the time. The other approach, which is dominantly used, is sliding window-based approach. So in sliding window-based approach, we are trying to answer this question. Okay, one extreme end, stop and wait, waits for an acknowledgement for every frame transmission. Okay, that means the sender has to wait for an acknowledgement before transmitting the next frame. On the other extreme end, like what we have discussed in the previous tutorial, what we can do is you send all the frames, then get only one acknowledgement. That's also a not good idea, right? Send all the frames means already the sender is jamming the receiver, right? So now we strike a balance, a trade-off. Can we keep the number of outstanding frames to a small value, some finite value? That is the number of outstanding frames. What do you mean by outstanding frames? Those frames which are sent by the sender but not yet acknowledged. These are the outstanding frames. In the case of stop and wait, the number of outstanding frames is 1. Okay? It can send only one frame. You cannot send the second frame before receiving the acknowledgement. But now, in sliding window, later you will understand why it is called sliding window. Okay? We allow up to W number of outstanding frames. That is, we permit the sender to send more than one without waiting for an acknowledgement. Okay? But that number should not be too high. Let's say W is 7, just an example. That means sender can send first frame, second frame, third frame, up to 7 frames without waiting for an acknowledgement from the other side. Okay? If the acknowledgement is not received, even after it sends out the 7th frame, then it will wait. Okay? So that way, it's trying to overcome the limitation of the sender. Okay? Because now there are many outstanding frames. That means sender is sending multiple frames, of course, one by one, serially, okay, without waiting for an acknowledgement. We need to give some sequence number for each frame, because when the acknowledgement is received, the sender should know which frame is acknowledged, whether 5th frame is acknowledged or 4th frame is acknowledged, or frame number 0 to 7 is acknowledged, so it should know which frame is acknowledged. So for that, we need to attach a number called sequence number as part of the header, in the header of the frame. Let's say this is the frame, let's say this is the payload, and this is the header. And in the header, K bits are used to represent the sequence number. The header carries information like destination address, source address, etc. Right? In addition to that, it also carries sequence number, few bits. For example, if K equal to 3, that means the frames are numbered from 000 to 111. Is that fine? So if K is 5, that means it is numbered from 0 to 2 raised to power 35. 5 minus 1, that is 31. Then it will be cyclic. Modulo 2 power K. 0, frame 0, 1, 2, 3, frame 7, again frame 0, 1, 2, 3, 7. Note that this frame 0 and this frame 0, they are different, even though they carry the same number. Okay? Acknowledgement, okay, acknowledgement is also a frame that also carries the sequence number that will tell which frame is acknowledged. Okay? And usually in practice, we use cumulative acknowledgement. Cumulative acknowledgement means the receiver need not acknowledge every individual frame. It can acknowledge a group of frames at once. Let's say it has received 5 frames. Right? It's receiving frames continuously. Okay, so once it is processed, process means, let's say, it's sent to the upper layer or passed to the next one. That means the processing is done. Once the frames are received, and the receiver side it is processed, then it has to send an acknowledgement. Right? So it will send acknowledgement for individual frame or a group of frames. When it sends When it sends a single acknowledgement to acknowledge multiple frames, we call it as cumulative acknowledgement. And we use this notation. This notation follows TCP notation. Some books will follow a different notation, but please note for my course, I am following this notation. So I expect you also to follow that notation. Okay, it's only a notation. Concept-wise are similar. Okay, what is the notation? We use ACK-N or RR-N. Acknowledge N or RR receiver ready N means that the receiver is ready to receive frame N onwards. That means it is acknowledging the receipt of the previous frames. Okay? So RRN means what received N-1, N-2, N-3, etc. Does it mean that it received frame number N? It's ready to receive frame number N. Okay? So RR5 means it acknowledges that it has received frame 4, frame 3, frame 2, frame 1, etc. Is that clear? And it's ready to receive frame number 5. Some books may follow the other notation. RR5 or ACK5 means it is acknowledging frame number 5 or up to frame number 5. No, I'm not following that notation here. Okay, now let's see how it works and why it's called sliding window, why the name sliding window, etc. On the center side as well as receiver side, both they keep a window of size W. Please note, when we say window of size W, there's no physical window or anything. Okay, it's just a software program. Okay, don't get confused. It uses some window and all, right? It's just a simple variable W. It uses a variable W. Okay, so let's say this is the sender and this is the receiver. So assume that W equal to 7. So many times I use the number W equal to 7. Okay, so later we will answer why I should not use W equal to 8. That is 2 cube, right? Okay. So first it sends frame number 0. When it sends frame number 0, W becomes 6. So initially W is 7. When it sends one frame, the value of W is some variable in the program. Okay, that is decreased by 1. W becomes 6. So we say that window shrink by 1. Window is shrinking by 1. That means W equal to 6. What does it mean? Initially W equal to 7 means the sender is permitted to send up to 7 frames without waiting for an acknowledgement from the other side. Now it has sent 1 frame. The quota is over. Quota is reduced now. It has already sent 1. So that means it is permitted to send 6 more frames. Permitted to send 6 more frames without waiting for an acknowledgement. So when it sends, let's say frame number 1, then here W becomes 5. Frame number 2, W becomes 4. Frame 3, W becomes 3. Frame 2, W becomes frame 4. Frame 4 means 0, 1, 2, 3, 4. 5 frames were sent. So it can send only 2 more frames. So window is shrinking. Right? Now, let's say it receives an acknowledgement. It receives an acknowledgement. When it receives an acknowledgement, the window will expand. If I don't tell anything, let's say it's receiving acknowledgement for 1 frame. Let's say the receiver is acknowledging 1 frame. Then now window will become 3. Window will become 3. It will expand because it received some acknowledgement. So in other words, whenever a frame is sent, window shrinks by 1. That is, W is reduced by 1. Whenever an acknowledgement is received, window expands by 1. Okay? And in extreme case, let's say F0 is sent, F1, F2, F3. Let's say 7 frames were sent, then W becomes empty, 0. When W becomes 0, then the sender has to wait. It cannot send any new frame because the window is exhausted. Okay, it's permitted to send only 7. It has already sent 7. After receiving the acknowledgement, it will proceed. Okay, I say window expands by 1, but if you use cumulative acknowledgement and the acknowledgement acknowledges, let's say, 4 frames, then window can expand by 4. It depends on how many frames are acknowledged. Right? And usually the sender keeps the frames in its buffer which are not yet acknowledged, because these are the outstanding frames. It may so happen that there could be errors and other things. So until they are acknowledged, the frames should be kept in the buffer, okay, because for retransmission purpose. The receiver side, similar thing is happening. It also keeps a window of size W. Again, it's also a simple variable count W. That means the receiver, okay, initially W equal to 7. That means it can receive up to W frames, and it can keep it in its buffer without sending an acknowledgement. That's what it means. So when frame 0 is received, then window shrinks, it becomes 6. That is, it can receive 6 more frames. Maybe you can equate to this the amount of buffer. When W equal to 7, that means it has a buffer to keep up to W frames. When a frame is received, window becomes 6. It can receive only 6 more frames. Then when frame 1 is received, W becomes 5. Frame 2 is received, W becomes 4. Right? Now, let's say it has processed that's all these 3 frames, 0, 1, 2. All the 3 frames are processed. Then it will send RR3. RR3 means it's ready to receive frame number 3 onwards. So it is implicitly acknowledging frame 210, the previous frame. So in that case, actually it is acknowledging, because there were 3 frames in the buffer. When it says RR3, note that RR3 doesn't mean it is acknowledged. This 3 doesn't mean it is acknowledging 3 frames. Okay, it means that it is acknowledging the previous frames. It so happens that the number of previous frames here is 3. Right? Now W becomes 7. Okay, now it has buffer to hold 7 frames. That's what it means. Okay? So whenever frame is received, it's put in the buffer until acknowledgements are sent, because it has to process it. When I say process it, it has to send it to the next layer. Okay, if next layer is not taking or reading or is not able to send further, then it cannot send an acknowledgement. Okay? Now let's look at this illustration. Now you will understand why it's called sliding window. Okay, again, there's no window to slide, right? It's a simple program with a simple variable, manipulation of variable W. Okay? Let's say this is the figure at the top is sender's window. Bottom is the receiver window. Okay, in this example, okay, I take it from the book, okay, but it so happened that the state, the window size, and the numbers inside are same for both sender and receiver. But in practice, note that initially they may be same, but after some time, the window at the sender and window at the receiver need not be same. See, for example, window at the sender may be 5. Window at the receiver may be 4 or 6. Okay? It's just for simple illustration purpose to start with. So this is a notation also we use. So you can see that these are the frame numbers, frame sequence number 0, 1, 2, 3, 4, 5. These frames were already sent out and they were also acknowledged. How do we indicate that they were already acknowledged? By using the thick vertical bar for illustration purpose. So this shows that before this, all these frames were sent out and acknowledgements were received. And you can see that there's a window here, and between the window and the vertical bar, there are 2 numbers listed, 6 and 7. These are the outstanding frame. Outstanding frames means 6 and 7 were sent out, but acknowledgement not yet received. That's what it says. These frames are put in the sender buffer until acknowledged. Acknowledgements not yet received. Because acknowledgements not received for these 2, the window size is 5 here. 1, 2, 3, 4, 5. That is, the sender is permitted to send 5 more frames. What are those 5 more frames? Frame number 0, frame number 1, 2, 3, 4 can be transmitted without waiting for an acknowledgement. That's the meaning of this. Okay? Similarly, on the receiver side, you can see a vertical bar here. Prior to this vertical bar, these numbers, they indicate that the frames already received and the frames were also acknowledged. Acknowledgements have already been sent out. Is that okay? And these are the frames which are received, which are currently in the buffer, but acknowledgements are yet to be sent out. Okay? It has not yet sent the acknowledgement. And the remaining numbers within the window, these are the frames which it could possibly receive in future. But it can receive only 5 more. Say W equal to 5. Because initially 7, it has already received 2, so now W equal to 5. Again, as I said, this illustration both show the same state, it need not be. Okay? Now, what will happen at the sender side? Let's say sender is sending the next frame, 0. That means the window will shrink, right? From this end. 0 will be here. 6, 7, 0 are the outstanding frames. Let's say now it sends one more frame. Now the window is here. It becomes smaller. If an acknowledgement is received, the window will expand from this side. Window will expand whenever acknowledgement is received. So whenever a frame is sent, the window will shrink from this side. Whenever an acknowledgement is received, the window will expand from this side. So it resembles sliding window. That's why it's called sliding window. Okay? Otherwise, in terms of implementation, it is just incrementing and decrementing a simple variable W. That's all. Okay? Similarly, the receiver also, whenever it receives a frame, it shrinks. So when it receives frame number 0, this window becomes size, the window size becomes 4. Then again, when it receives another frame, this becomes smaller. Whenever it sends an acknowledgement, let's say it sends an acknowledgement for 2 frames, because 2 frames have already been processed, then it will expand by 2, this side. So again, on the receiver side also, the window is sliding. Let's look at one more illustration. Let's say A sends frames to B. Okay, we show this snapshot of a few transmissions and acknowledgement, transmission of the data frames and acknowledgements. And please note that we are not showing all possible states here. Just we show some state for you to better understand. Okay? So initially, assume that W equal to 7 on both sides. So you can see that the vertical bar is here. That is, no frame is sent. Similarly, no frame is received. Let's say sender sends frame 0, 1, 2. So when it sends frame number 0, window will become like this. It will shrink. Frame number 1, it will shrink further. Frame number 2, it will shrink further. So after it sends frame 2, this is the window. Window is 4. You can see that between the vertical bar and the window, 3 frames listed, 0, 1, 2, because these are the frames which were sent, not yet acknowledged. In other words, these are the outstanding frames. So when these frames are received, when frame 0 is received, the window will be updated like this. Window will shrink. Frame 1, it will be shrinking here, here. After receiving these 3 frames, window will be something like this. So here, 0, 1, 2 are the frames which were received, but not yet processed, acknowledgement not yet sent. That's what it means. Let's say at this time, it sends RR3. As I said before, RR3 does not mean that it is acknowledging 3 frames. RR3 means that it is acknowledging all the frames prior to number 3. It is ready to receive from 3. So as per the current state of this receiver, before 3, 2, 1, 0, 3 frames are there. So when it sends RR3, okay, it's acknowledging 3, so it will expand by 3. So you can see that now W becomes 7. And this vertical bar has moved here because nothing is outstanding. It has cleared out. It has sent acknowledgement for everything. Any doubt? Yes? We will discuss the possible cases later. Yes. Okay. How protocol take it. Yes. Please be louder. Yes. Okay. Good question. Okay. So what you suggest is let the full window be used, then send an acknowledgement. Right? That means once when we say full window is used, then the entire 7 frames have already been sent out. Right? That means the window is empty at the sender. So after sending 7 frames, it has to wait for an acknowledgement, right? Even though the link is free, it cannot send any frame. Even though the link is free, the sender cannot send any new frame because it has exhausted the window. It has sent all 7 frames and it has not received the acknowledgement. So what you suggest is the receiver can send an acknowledgement after receiving all 7 frames, right? So that means sender has already sent 7 frames. So there is a small delay, right? So this is frame 0, frame 1, that's what you suggest. This is frame 7, right? So the sender, at this point, the sender window becomes 0. Sender window becomes 0. So sender cannot send anything, even though the link is free. The last bit of frame 0 has to travel to reach the receiver, correct? So as per your suggestion, the receiver will send an acknowledgement now. Then it will take another TP. Then only at this point, the acknowledgement will be received by the sender, right? So during this time, the sender is sitting idle. When it is done with the processing. It receives the frames, put in the buffer, okay, when it is done with the frames, right? There could be different design principles, okay? So whenever it processes 1 frame, it can immediately send an acknowledgement. Other possibilities, whenever it processes multiple frames, okay, it can send an acknowledgement. Or it can wait for some time, okay, it processes all the frames, then send an acknowledgement. Who? The receiver, is it? Okay. I think you might have got confused because sender and receiver, even though we say connected by a link, I think as I was mentioning, there are 2 fibers inside, okay? So the transmission from A to B takes place on 1 fiber, and B to A, the acknowledgement comes, this is transmitted on another fiber. So there is no question of link is free for that, okay? Is that clear? Now, let's say sender transmits, let's say F3, F4, F5, F6. Just an example, after sending 4 frames, this will shrink by 4. So now here it is 7. Why it is 7? Because when RR3 is received, the sender looks into the state. So it knows that the receiver is acknowledging those frames before 3, that is prior to 3. So that means these 3 frames are acknowledged. So it will expand by 3. So it has expanded. It is expanded by 3 here. W is 7. Then now after sending 4 frames, the W will become 3. Now 3, 4, 5, 6 would be the outstanding frames. Now at the receiver side, we show the state of the window after receiving F3 and after sending the acknowledgement. When F3 is sent, or F3 is received by the receiver, the window shrink here. Window will be something like this. Now, when it sends an acknowledgement, okay, this is not shown actually. So maybe at this point, this will be something like this. The vertical ball will be here. 3 will be here. 4567001 will be here. Now, okay, this is the window at this point. Now it sends RR4. RR4 means what? It's acknowledging the earlier frames. Earlier frame means here is only one frame which needs to be acknowledged. So it is expanding by 1. So it is expanded by 1. So this is the state after it sent RR4. Is that fine? Now, when RR4 is received, note that RR4 doesn't acknowledge 4 frames. RR4 says RR4 is not acknowledging frame number 4. RR4 is not acknowledging 4 frames. RR4 acknowledges the frames prior to 4, frame 3, 2, 1, 0, etc. Okay? So when it is received, here, before 4, there is only one frame, 3. Right? The receiver says it's ready to receive frame number 4 onwards. So this is the state of the center when it receives RR4. So before 4, there's only one frame. So the center will expand by only 1. So W becomes 4. And the vertical bar from here will be moved here because 3 has been acknowledged. Okay? Any doubt? Yes? Here? Yes, it's possible. This is called cumulative acknowledgement. Cumulative. Cumulative means it's acknowledging a group of frames. So it's only one frame, one acknowledgement frame, and the sequence number will indicate 3. That means the receiver is ready to receive frame 3 onwards. Implicitly, it is acknowledging frame 2, 1, 0, all the previous frames. That's possible. Okay? Yes? No? Yes? Okay, that we will discuss later. Okay, that how to deal with errors. Okay, so right now we assume there are no errors. Okay, just let's understand the basic concept. So when there are errors or the losses of the frames, even the acknowledgement can also be lost. Okay, so how we can deal with, how the protocol deals with that in addition to the flow control. Okay, that we call it as ARQ, automatic repeat request. That we will discuss at a later part of the lecture. Yes. Okay, that's a good question. So window, we are not using 2 cube, right? Less than 2 cube, right? So that is, of course, in tutorial, next tutorial, right? Next week tutorial, not this week. This week tutorial is for the last week's lecture, okay? Tutorial number 3, we will have a problem, why it should not be 8, why it should be less than 8, okay? So maybe intuitively, okay, we can understand, or I can explain quickly. When an acknowledgement is received, okay, sometimes there will be confusion whether it is acknowledging frame number 3 in the current window or frame number 3 in the previous window. Because it's repeating, number is repeating, 0, 1, 2, 3, 7, then 0, 1, 2, 3, 7. This frame 0 is different from this frame 3, 0. This frame 3 is different from this frame 3, though the frame number is the same, right? So if you keep W equal to 8, there are situations where when an acknowledgement is received, the sender will get confused, whether it's acknowledging frame number 3 in the current window or frame number 3 in the previous window. Right? So to avoid that confusion, okay, window size is kept at least one smaller than 8. anything, 8. If there are no errors, that problem will not come. But anyway, we just keep that convention. I can use W equal to 8. In that case, I should use sequence number, 4-bit sequence number. If the frames are numbered from 0 to 15, okay, I can go up to W equal to 15, not more than that. W equal to 16 cannot be used. So there are some enhancements to sliding window. So again, the sliding window is top and wide. So what is more important is the understanding of the concept. Of course, to answer some questions, we follow certain convention. We stick to the convention to avoid multiple answers or for me to understand that you have correctly understood the concept, okay? But there are some enhancements when they are implemented in practice. There could be variations. So later also we see, okay, how the errors can be handled, okay, when a frame is missing, what should be done, this, that, what type of messages can be exchanged. So they are all the basic suite of messages and the operations. But there could always be enhancements or variations of the sliding window or stop and wait when we are actually implementing it. But the underlying concept will remain the same. Okay? Let's look at some enhancements. We can, or a network can introduce, okay, a new message which, let's say, which says receiver not ready. So far we have used RR, receiver ready. RR5 means receiver is ready to receive frame 5 onwards, right? Now RNR5 means receiver acknowledges the previous frames, 4, 3, 2, but not ready to receive from 5. That means it asks the sender, don't get confused, just keep waiting, okay? I'll come back to you again after some time to proceed further. So until then, you wait, okay? Don't probe me what is happening or anything, okay? You wait until I send another acknowledgement. So I can use R and R to indicate that. So note that when we say protocol is message plus operation. What type of messages are exchanged? When a message is received, what is done? That together will define a protocol. To put it in simple way, okay? That's why in lecture notes part 2, if you look at, when I say message, it's a horizontal peer-to-peer interface. You are exchanging some messages. Okay? So next, in the case of duplex communication, which is the normal or practical, okay, in the switched networks, piggybacking method is normally used. What is piggybacking? Let's say this is sender, this is receiver. So there's a link connecting these two. The communication is duplex, full duplex. That is, A can send it to B, B can send it to A at the same time. Okay? But how it is implemented? Usually it's implemented by 2 different fibers. Okay? So, of course, we can transmit same time on the same fiber, but technologically, okay, maybe more challenging and maybe more expensive. So better we go for 2 fibers. Okay? So now the question is this. When S can send some data to R, okay, the receiver can also send some data frames to S, right? It's not that only S is sending data frames, R should always send acknowledgement frames, right? R also may want to send some data frames to S. In that case, S has to send acknowledgement frames to R. That means S is sending some data frames, R responds with acknowledgement frame, okay? Or maybe you can call it as A and B. A can be sender as well as receiver. B can be sender as well as receiver, right? So what is done is this. In the frame, let's say the frame format, let's say we have payload, and we have k-bit sequence number. In addition to k-bit sequence number, we also use another k-bit acknowledgement number. Okay. What is done is, when the receiver sends an acknowledgement, it's not sending a separate acknowledgement frame. Instead, it sends the acknowledgement number as part of its own data frame. So let's say, now look at this example. A sends data frame F3 to B. A sends a data frame, which is frame number 3. Now B receives it. B receives it. Now B will send, okay, let's say this is frame 3. Let's say B sends RR4. RR4 is ACK4. Now the question is, should it send a separate RR4, or if it has a data frame, it can piggyback it. It can ride on it. It can ride on it, okay? So let's say B sends a data frame 6. B has some data frame number 6. So in that case, the receiver will send this frame to the sender, where the sequence number will be 6110, and the acknowledgement field will be 4. So when the receiver receives this frame, it understands that it's receiving RR4, and also it is receiving the data frame, which is number 6. Is that okay? This is just to avoid a separate acknowledgement frame. Now, there could be other questions. Suppose receiver has no data frame to send. We cannot say that receiver has always some frames to send, right? If it has no data frame to send, it can send usual separate acknowledgement frame, as usual, okay? RR4. If the receiver has data frame, receiver has to send some data frame, but it has not received any frame from the other side. Let's say earlier it received frame number 3, so it sends RR4, right? Now the receiver is sending another data frame, but it has not received any new data frame from the other side. So in that case, it will simply repeat the same RR4 again and again. Hi, I'm waiting to receive 4. I'm waiting to receive 4. That is what is given here. So these are all possible variations or enhancements. We can also come up with some new variations, okay, which would work good. That's fine. Any doubt? So now let's move on to the next part, that is reliable transmission, error control and reliable transmission. So far we have seen flow control in the context of no errors, no damage, frame damage, no loss of frames. Now we are going to incorporate the errors and losses into that, how the protocol can be modified, or what additional frames are required, what should be done when such messages are received. Okay. First, the receiver should be able to detect the error. That we have already seen, right? Usually, almost all link level protocol, they use CRC, cyclic redundancy check method, which we discussed in the previous lecture, to detect error. That will be there. Correction of errors, they don't do it. They don't correct it. So when there is an error, the frame is dropped. Yes. In addition, okay, the simple way is frame is dropped, don't do anything. Don't do anything. If you take Ethernet, it simply drops it. That's all. But at the wide area or point-to-point link level, okay, there are protocols which do error control as well, in the sense that after dropping, it may request the sender to transmit again. So if it asks the sender to transmit again to make sure that it has reliably or it has correctly received the frame, then we call it as it is reliable transmission. Note that it is optional at link level. If it is not done at link level, it will be done anyway. It will be done at the TCP level, at the connection level. Okay? But you can easily compare. When you do retransmissions at link level, let's say link 1, link 2, link 3, link 4, this is one possible way. You can do retransmissions at the end host level. That means if something is missing, whether the frame is dropped here, that will not be detected. Sorry, that will be detected, they just dropped. That will not be retransmitted at link level, but only this destination host, the source host, will ask the sender to send it. So if you don't do retransmission at link level, layer 4 will do it, but the drawback here is that, let's say the frame, the error is here on this link, or in this link, or this link. In either case, if it is done at the link level, only on that link it is retransmitted, right? Let's say there's an error here. The retransmission is only between these two. But if retransmission is here, the retransmission, the new frame should go through all the links. Is that okay? That's the difference. So we will consider two type of frames, lost frame and damaged frame. As I mentioned in the beginning, damaged frame means the frame is received, CRC test failed. Lost frame means something is received, some bits signals are received, but the receiver is not able to recognize that it's a frame because during the propagation it was heavily affected by the noise, it's heavily damaged. Okay, that we call it as lost frame. So the protocol which implements this flow control plus error control, I mean dealing with the errors as well for retransmission, we call it as ARQ, or automatic repeat request, ARQ. As the name says, if there's an error, it is detected, then it asks the sender. Sender means sender of the link, on the link, to retransmit. Okay? So when I say, as I said, protocol, here we have few functions or operations and messages. The messages are this: acknowledgement RR, which we call them as positive acknowledgement. That means if there is no error, it sends RR3, RR5, ACK3, ACK5, no problem. Okay? In addition to this, we will use negative acknowledgement. That means when the receiver finds that there's an error, let's say CRC test has failed, it may send something like negative acknowledgement. These are different names. Reject, I can say reject 5. I'm rejecting frame number 5. Okay. Selective reject. I'm selectively rejecting some frame. So these are some naming conventions. So in addition to the RR frames, RR acknowledgement frame, we use some negative acknowledgement frames as well. Okay. Then, so obviously error needs to be detected. There should be error detection mechanism. That's a part of it. And more importantly, there should be a mechanism which we call it as timeout. So timeout means how long the sender can wait. Sender has sent something. There's a small probability, okay, that the frame is lost or damaged, and the other party sends response to something that's also lost. Correct? You can always come up with different such scenarios where sender has no clue what's happening. Sender has no clue of what is happening. So that we call it as timeout. That means associated with a sending event, we associate a timer locally. When it expires, that means it can wait for this much time. If it doesn't hear about this, about the acknowledgement within that time, it will time out and it has to take some new action. So we look at two approaches again: stop and wait ARQ, then sliding window based ARQ. The sliding window based ARQ, there are two ARQ we are going to look at. One is go back N, then selective reject. So there's a difference between go back N and selective reject. And go back N, both are based on sliding window. Okay. In the case of go back N, the maximum window size is 2 raised to the power k minus 1. That is, if k equal to 3, frames can be numbered frame 0 to frame 7. But in the case of selective reject, this is slightly different. If k is the number of bits in the sequence field, maximum window size is 2 raised to the power k minus 1. That is, if k is equal to 3, we can have f0 to f3 only. F3 and F4, right? 2k power minus 1. That means 2 square, F4. Not more than that. Okay? And for this, we look at a tutorial problem, next week tutorial. For this, I think you can refer any book, similar example. It's not a formal proof. I'm not interested in mathematical proof. But we prove by what is called contradiction, okay? Like we assume that W equal to 8 is possible, then we make an argument, then it will lead to the case that that cannot happen, right? So that is a proof by counterexample or proof by, of course, I'm not going into the theory of that. What should be the window size? Forget about these numbers, because sometimes these numbers are given book, maybe based on old data or something. Let's say you have a short link and a long link. How the window size should be chosen? Okay. Suppose it's a high-speed link. High-speed link means B, large bandwidth. Long distance mean D, the delay, propagation delay is longer. Suppose the link is longer, that means propagation delay is longer. If it's a high-speed link, let's say data rate or bandwidth is quite high. In that case, we should have a large value for window. Now you just imagine, if the window size is small for a high-speed, long-distance link, what will happen? Because the data rate is high, frame transmission is faster. Quickly it will transmit, right? Frame 0, frame 1, frame 2, very quickly it will transmit. So it can quickly exhaust the window. If the distance is quite long, it takes long time for the acknowledgement to come back, right? So if the data rate is high and it takes long time for the acknowledgement to come back, the window at the sender side would be quickly exhausted. Window becomes empty. That's not a desirable one, because when window becomes empty, we cannot proceed further. Okay? So usually, if you look at in terms of the bits, okay, by the time the acknowledgement comes back, we still want the window to be non-zero. Window should not be empty when the acknowledgement comes back. So in that case, window will always, even though it shrinks, before it becomes empty, it will expand. Okay, that means window will never become empty. That's the situation we want. We want to continuously transmit to utilize the link better way, right? So usually we expect the window size greater than dB product. Okay. If it's smaller than dB product, by the time the acknowledgement comes back, window will become empty. Of course, similar things you will be studying in TCP as well. Sometimes students get confused because in TCP, we don't work in terms of the frame, or we don't work in terms of the packets or segments. It works in terms of the byte, assuming that each byte is numbered, byte 0, byte 1, byte 2, something like that. There will be, it uses a sliding window, okay, not stop and wait. So similar things you will be studying there. It's good to study different link level. We look at the frame perspective, okay, and TCP level we look at it from the byte perspective, okay, and also in terms there are other differences as well. For a link, you can estimate the round trip time easily, right? For a link, it's fixed, mostly fixed. You know the length of the link, you know the round trip time. So you can have, you can estimate approximately within this time, we can expect an acknowledgement. Some bound we can at least we can estimate. But for the TCP, since it goes through multiple links, multiple routers, okay, there could be queuing delay at different routers. So the round trip time or the propagation time cannot be easily estimated. It's a challenging task. So if you ping a remote server, now maybe after some time, afternoon or after 1 hour, 30 minutes, or even after a few minutes, you will get different values. The round trip time will be different at different times, even to the same server, okay? So TCP, that's more challenging. There are methods, okay, how we can estimate. I don't know whether it is taught or not, how we can estimate RTT and other things. But those things we don't study it here because RTT is known. It can be easily estimated for a link. Right? Let's start with stop and wait ARQ. So this works similar to stop and wait. Sender sends a frame, okay, and the last bit is transmitted here. It takes TP time units for the last bit to travel to the other side, another TP time units for the acknowledgement to come back. Then it sends next frame, then next frame. This is 2 TP. That's how it goes. Now the question is, if a frame is lost or damaged, what should be done? Stop and wait uses simple mechanism. It uses timeout. The simple way is the receiver will send an acknowledgement when it receives and processes it. If it doesn't receive anything or it receives a damaged frame, simple way is it doesn't need to send anything back. So obviously the sender will time out. Now look at this. Frame 0 is sent. It responds with RR1, that is ACK1. That means the receiver is ready to receive frame number 1. Okay? Note that since we are waiting for an acknowledgement for every frame, you can just use 1-bit sequence number. That is sufficient for stop and wait. That means we use frame 0, frame 1, frame 0, frame 1, frame 0, frame 1. Because the sender can transmit to the next frame only after receiving the acknowledgement of the previous frame, just 1-bit sequence number is fine. F0, F1, F0, F1. Is it okay? Because when it receives this F0, it should go through this F1, right? This F0 is different, obviously. So that's why it says frame 0, RR1. Frame 1, it says RR0. Now frame 0 is lost or even damaged also. So see that the receiver is not responding with any message. So sender times out. It waits for a certain amount of time. That depends on the round trip time, the length of the link, okay? How long it can wait. It should not be too small, then it will be a false timeout. It should not be too small, it should not be too long, in that case it's a waste, right? It should respond at appropriate time. Then if it doesn't receive the acknowledgement, it simply sends retransmits frame 0. Now it receives this, it responds with ACK1. Now look at this situation. It sends frame 1. The receiver responds with RR0, that is ACK0. That means ACK0 means it is acknowledging the previous one, that is frame number 1 is acknowledged. But this acknowledgement frame is lost. I think this type of questions some students were asking here. Okay, if the acknowledgement is lost, the sender has no clue. Sender is not receiving, it times out. When it times out, it doesn't know whether the frame was lost or acknowledgement was lost, right? It sends something, it's not receiving anything from the other side within that timeout period. Okay? So to be on safe side, it will transmit the same frame again. In the previous case, also it timed out, frame 0 it sent, frame 0 it's repeated, there's no issue. Why? The frame was lost, so it has to send the same frame. But here frame 1 was sent, it was received. It was the acknowledgement which was missing. Is it okay? So, but even in that case, sender has to transmit the frame again. This is frame 1. So frame 1 is sent here, frame 1 is sent again. Now the receiver will find out that this is a duplicate frame. How it knows it's a duplicate frame? It does not need to compare the previous frame and the new frame, right? Even if it compares the previous frame and the new frame, just because the bits are the same, we cannot say it's a duplicate frame, right? Very simple, because it sent out ACK0. It sent ACK0, that means it's expecting frame number 0. It is expecting frame number 0, but it is receiving frame number 1. Then it will understand that the sender by mistake, or to be on safe side, it has sent a duplicate frame. So that will be rejected. Any doubt? Which one? Receiver usually don't. We don't need to. If you want to implement that, but I don't think that's necessary. Sender, because sender is the one who is going to retransmit, right? Receiver most of the time simply keeps quiet to let the sender time out. Sometimes later in sliding window, okay, it may also send a reject. Okay, if it knows that, okay, this frame is received, it is damaged, then it can tell the other party, hi, I received frame number 5, but it is damaged. Okay, can you send frame number 5 again? Otherwise, automatically there will be a timeout on the sender side. Pros and cons, as usual, stop and wait means the implementation is simple. And drawback or limitation is link utilization is poor. Why link utilization is poor? See, we transmit only during this time, right? And during this time, there's no transmission on the link because the sender is waiting for the acknowledgement, right? So the total time is something like this. When the link is available, this much time the link is available, but out of this, we are making use of the link for transmission only during only this time, short time. So the ratio between the frame transmission and the total time will give you the link utilization. Ratio between the actual time spent for transmitting the given data frame and the total time the link is engaged or the link is available for it to transmit. The link is available for it for longer time until this, for one frame. So if you want to calculate for 100 frames or anything, you can add this time, this time, this time, this time, all this time, okay, the link was available. But the link is used only during this time. So link utilization is poor. So now let's move on to the next type, sliding window based ARQs. So there are two variants. One is go back N, the other one is selective reject or selective retransmission. We spend more time on go back N, then I will highlight the difference between go back N and selective reject. It's based on sliding window, so whatever mechanism we used for sliding window flow control is also applicable for this. Okay, so if there is no error, like the flow control protocol, it works. So it sends RR acknowledgement frame as usual. If there is an error, what happens? If there is an error, what happens? Let's say frame 0 is sent, frame 1 is sent, let's say frame 2 is sent. Let's say frame 2 is damaged error. So that means the CRC test failed for frame number 2. So it may send an acknowledgement for this. At this time, it sends a negative acknowledgement, reject 2, reject number 2. When you say reject 2, this means that the receiver is rejecting 2, receiver asks the sender to retransmit to 2. But when it is received at the sender would have transmitted some more frames, like frame 3 and frame 4, right? So what the receiver does is this. Because it found frame 2 was damaged, the receiver is quite adamant, it will not accept any new frame. Frame 3 is rejected, frame 4 is also rejected. So it will wait only for the damaged frame to be correctly received. That means it wants only frame number 2. It will not accept any new frame. Frame 3, frame 4, not accepted. So what the sender does is, it receives reject 2 only here. Okay, so it has to retransmit frame number 2, right? It retransmits frame number 2. But it knows that go back N is used, that means the receiver would not have accepted frame 3 and frame 4, so it will retransmit frame 3 also, frame 4 also. Even though frame 3, frame 4 were good frames, When it receives reject 2, the sender goes back to 2, frame number 2, it will go always in sequence. Is that clear? It goes back to 2, then it will send 2, 3, 4. Even though 3 and 4 are good frames, that will be retransmitted again. So on the receiver side, 3 and 4 are good frames, CRC test, pass, whatever it is, it will not accept it. So this simplifies the operation, making sure that everything is received in sequence, no need for sorting or reordering the frames, right? Because it expects always in order. If when it comes out of order, it will not accept it. So it wants 2 before it expects 3. Is that okay? That's why it's called go back n. That is, when the sender receives reject 2, it goes back to 2, then starts from there. So you can see the important concept here. Receiver discards that frame and all subsequent frames until error frame is received correctly. Sender goes back and retransmits that frame, that is that damaged frame, and all subsequent frames. Is that okay? Now let's look at few scenarios. Of course, there may exist more than these scenarios to handle the possible errors. Let's say receiver detects error in frame number I. Receiver detects error in frame number I. Let's say I equal to 2. That means receiver sends reject 2. It sends reject I. And it discards any new frame received until frame I is correctly received. That's what we have seen. Frame 3, frame 4 all discarded, rejected. Now sender gets reject 2. Let's say reject 2, reject I. Assume that I equal to 2. Now sender retransmits frame I and subsequent frames. So it will retransmit frame 2, frame 3, frame 4 onwards. So that's how the damaged frames are dealt with in go back n. Now let's look at the case of lost frame. Let's say frame I is lost. Assume that I is equal to 4. Frame I is lost. This is lost. It may so happen that the receiver has received frame 3, and the next frame it receives is frame number 5. Because frame 4 was lost in the sense it could not be recognized as a frame. Right? So frame 3 was received, frame 5 was received. So receiver understands that this is out of order. After 3 it is receiving 5. That means 4 was lost. Frame number 4 was lost. So what it will do? It will send reject frame number 4. So reject 4. Reject 4 will be sent. Is that clear? So in the previous case, it's a damaged frame. The CRC fails, it knows that frame number 2 has an error. Now, frame number 4 was lost. It's not able to carry out even CRC test. So frame 3 was received, frame 5 was received, now it sends reject number 4. Okay? So what sender will do? Sender will send, receiver sends reject I, sender will go back to frame number I and all the subsequent frames. So this, okay, even though it has already sent frame 5 and frame 6, the sender will repeat all those things. Maybe I look at this example here, illustration here. So frame 2 is received, frame 3 is received, frame 5 is received. So after frame 3, frame 5 is received. So frame 4 is missing. So now receiver infers or understands that frame 4 was missing, so it sends reject number 4. Reject number 4 is received here. This is the time. Okay. So the sender will send frame 4, but it will go back to frame 4, it will continue from here. It will repeat frame 5, 6 also. Note that frame 5, 6 were good frames, but still it has to repeat. Is that clear? The concept of go back n. Okay, now here we assume that frame 3 was received, then frame 5 was received, right? But what happens if there is no frame number 5? Let's say after frame 4, there is no new frame sent by the sender. Okay, we cannot always say that sender will be sending the next frame, right? Maybe it doesn't have any new frame to send, or the window is exhausted. For some reason, it's not sending any new frame. So frame I is sent, that is second case. Frame I lost, sender is not sending any new frame. Sender is not sending any new frame. That means here 4 was lost, sender is not sending frame 5 or 6 anything. Maybe it doesn't have any frame to send. So what's happening? The receiver gets nothing, and the receiver also doesn't respond with anything, right? Because this frame was lost, it doesn't know, receiver doesn't know that that frame was lost. So it's not responding with anything. Eventually, sender will time out. When sender times out, it has to probe the receiver, hi, what's happening? Okay, it has to probe the receiver, what's happening, what is it you are expecting. The sender sends a special frame called command frame, that we call it as RR command frame, receiver ready command frame. Which frame you are ready to receive, that's what it wants to know. And that frame will have a bit in the header called pro bit, that bit is set to 1. So when the receiver receives this command frame, it's not a data frame, and it notes, if it notes that, okay, this particular bit is set to 1, that means the sender wants to know which frame the receiver is expecting. Now the receiver will respond with some RR, which frame it is expecting. If it is expecting frame number I, it will say RRI. Okay, if it is expecting something else, it will send, okay, RR, that number. So in this case, I was lost. So assuming that it has received I minus 1 until I minus 1, so it will respond with RRI. Hi, I want RR, the frame number I onwards. Then the sender will send frame I plus 1, I plus 2, etc. Is it okay? So there should be a timeout mechanism when sender is not receiving anything from the receiver side. There are other few cases which we can quickly look at. Go back and damaged or lost acknowledgement. Let's say receiver gets frame I and it sends RRI plus 1. Let's say this is F3 is received, then it sends RR4. Assume that this is lost, RR4 is lost. So it's receiving frame number 4, frame number 5. Then note that the receiver doesn't know that RR4 was lost, right? It received RR3, it sent RR4, sorry, it received frame 3, it sent RR4. I am ready to receive from 4. Does it know that RR4 was lost? Now it receives frame 4, frame 5. It sends a new acknowledgement, RR6. New acknowledgement, RR6, without knowing that RR4 was lost. Correct? Assume that RR6 is received by the sender. Will it pose any problem? Sender did not receive RR4, but it's receiving RR6. Will there be an issue? It's not an issue at all, because RR6 is a superset of RR4, right, as per the definition. RR4 means it's acknowledging all the frames prior to 4, 3, 2, 1, 0. RR6 means it's acknowledging all the previous frames, 5, 4, 3, 2, 1. So this is a superset of this, right? even though sender did not receive RR4, even though receiver doesn't know that it lost RR4, RR6 is received, there's no problem at all, no issue, right? So since the acknowledgements are cumulative, there's no issue. That is case 1. If RR6 is received before sender times out, that's no problem. Suppose RR6, this kind of command frame is received before it is received, sender times out. That might happen. If sender times out, the same procedure is used. The sender will send RR command frame. That's a command frame. One bit is set, that is P bit, probe bit is set. When it is received by the receiver, it will respond with, okay, I want this frame. Look at this. Look at this case. Frame 6 is received. It responds with RR7. This is lost. Then it receives frame 0. Of course, later it may respond with some other RR, but before that, it times out. If the sender times out, it responds with RR P bit set to 1. Now, when P bit is received, so RR command frame is received, the receiver will respond with which frame it is expecting to receive. Assume that it has received frame 0 and assume that it has already processed frame 0, then it will respond with RR1. Note that it lost RR7, but now it responds with RR1 because it has received 0, assuming that it has already processed 0. The latest one, the one is that it is expecting frame number 1. That's all. Now this will respond with frame 1, frame 2. Is that clear? So when we compare this with the stop and wait, this has better link utilization. Okay. And it is less complex compared to the next method, selective reject. Okay, because we say that go back and does not need to reorder it because it expects the frames always in sequence. Right? It doesn't need to, let's say it has received some frames here, and it's waiting for the missing frames to put it in order. No, we don't need to do that. Okay? But when compared to stop and wait, it's more complex. It's a good choice when the errors are rare. Why? Because in the event of error, the sender may have to retransmit good frames also. So if the error probability is small, we can go for this. Retransmission of error frames is obviously an overhead that reduces link utilization because it's not useful. Why it should unnecessarily retransmit the good frames? Right? So now, the next one is selective reject. I just highlight the difference between selective reject and the previous one. Okay, so the difference is this. In case of go back n, when let's say frame 0, let's say frame 1, frame 2, let's say frame 2, we assume that frame 2 is damaged, CRC test failed, it sends a reject 2, okay. Now selective reject will use another convention, selective reject 2, it sends selective reject 2. So by the time reject 2 is received, it might have sent frame number 3 and frame number 4. So what the sender does is, it doesn't go back to frame number 2, that is frame number 2 is retransmitted, there is no way because frame 2 was damaged. The next frame to be transmitted would be the good frame, next good frame. That is, it won't transmit 3 and 4, but it will directly jump to frame number 5 because 3 and 4 were already transmitted. Okay? That's a key difference. Maybe look at this case. Frame 3 is received, frame 4 was lost. Now the receiver receives frame number 5, so it infers, it understands that frame 4 was lost, so it sends selective reject 4. Selective reject 4 is received here. So it retransmits frame number 4. By the time it receives selective reject, it has already sent frame 5 and 6. So frame 5 and 6 will not be repeated. It will continue with frame number 7. So what the receiver should do is, Okay, it received 3, it received 5, it's out of order, and now it receives 5 and 6. It will not throw it, it will keep it in the buffer. So later that will put, when the missing frame arrives, it will put it in order. So it has to keep those frames in buffer until all are received in order. Okay? So this is the key difference. Otherwise, many other scenarios will work in a similar way. Any doubt? Students, any doubt? Okay, before we wrap up today, so we look at just one slide, parameter A. We don't have time to study the performance evaluation of the protocols, which we will do in the next lecture. Okay. So next topic is how we are going to measure the performance. Can we derive simple expression for link utilization for stop and wait and sliding window with error, without error, etc. Okay. We want to quantitatively compare the performance. We know sliding window is performing better than stop and wait. Right? Okay. So to do that, I just introduced some notation today. So we will derive the actual expression next week. Okay. We are going to derive link utilization. Okay. So link utilization, as we have seen before, this is the ratio between the actual transmission time and the total time, including the waiting time. Okay, what's the total time, including the waiting time, and what is the actual frame transmission time? That ratio will give the link utilization. We use this notation frame transmission time as TF. I think earlier we were using TT or something, but in this case we use TF. It's the frame transmission time. TP is the propagation time. And T total is the time link is engaged. Engaged in this means including waiting time and actual transmission time. What's the total time? That we use T total. Transmission time of acknowledgement frame is negligible. That's the assumption we are going to make. Of course, we can easily modify the expression if we do not make this assumption. So you should be able to modify this. Frame error probability is PF. Assume that a frame is damaged, lost with some probability P. Okay, how the expression is affected. And we also assume the errors in the acknowledgement frames are very small or neglected because it's a very short frame. And also in the case of go back N, errors in the retransmitted frames other than the original frames can be ignored. So we assume that only if this frame is damaged, when it is retransmitted, that is not damaged. That's the assumption we make. And we are going to use parameter A in our derivation, and easy to remember the expression in terms of small a for the test quiz, which is going to be in week 7. Okay, most probably on Wednesday, week 7, it will be conducted during the lecture. Okay, I will confirm it later by the announcement. So for the test, you are not allowed to bring any help sheet. For the final exam, you are allowed to bring one A4 sheet. Okay? For the test, you may have to remember some small expressions formula. Of course, very complex formula like the bandwidth of T3 link, those numbers I will give if needed, right? But some simple expressions you should know. Even if you forget, within a minute or few seconds, you can derive it. They are not difficult to derive. Okay? We are going to use A, parameter A, which is the ratio between link propagation time and frame transmission time. And A is also the number of frames that can be held on a link. You take a link, let's say A, B. There are many bits which are traveling on the link at any time. So if you look at in terms of number of bits on a link, that is dB product, if you remember. How many bits will be there on the link? That is dB. dB here is TP multiplied by B, because D here is nothing but the propagation time TP. So, but if you divide this into frames, how many frames can be held on a link at any time? Let's say when some frame is here, some frame is being transmitted here, right? There are many frames existing on the link. That gives small a. How? A is equal to TP by TF. This is equal to D by TF. So multiplied by B on both sides. So that's equal to dB product. dB product is number of bits on a link divided by size. What is TF by B? TF multiplied by B. TF is equal to size divided by bandwidth, correct? Transmission time is size divided by bandwidth. So TF multiplied by B is size. So number of bits held on a link is dB. If you divide it by size, you get number of frames that can be held on a frame. Correct? Number of bits is dB. You divide it by size of the frame, you get number of frames that can be held on the link. So let me stop here. I think we were, okay, that's fine. So next week, initially we spent some time to derive the expression, then we move on to Ethernet. And the last week we will discuss Wi-Fi, that is wireless LAN, that will be the end. Week 7 there will be a test, most probably on Wednesday during our lecture hour 1 to 2 p.m. I need to find the venue and all. So if I can find the venue, it will be held on Wednesday. If I cannot book a venue, maybe push to Saturday. If I cannot find the venue, okay? Right? It's not like makeup lecture. I can do it on Friday and webcast it. I cannot do it. So please wait for my email. Either this week or next week, I will announce it. Let me stop here. I can stay for some more time. Those who have doubts, okay, so I can spend time with you. Others can leave.